Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Aneel Sorumpudi, and in this session, we're going to discuss about an important topic in the entire operating systems, that is designing a hardware lock. What is this hardware lock, how it gets designed, how it is going to be implemented, we're going to completely see in this session. So let us start. This is all about myself. I do have a total of 13 years of experience and I taught everywhere in India including Andaman and Nicobar, and I'm a triple post-graduation holder. So let us start. This session is all about the actual critical section problem. We're going to recall what is critical section problem, right after which we're going to understand how a hardware lock is going to be designed. So let us start. Understand something before I explain you people about a critical section. You people will be the application developers. Right after you finish your graduation, you will be the software developers. In software developing, what is the regular job? Most of you people, 90% of the people are going to develop the application. What is an application? The application is going to comprise of several programs, several processes indeed, right? In those processes, understand something that most of the processes are independent, but some of the processes are cooperative processes. What is a cooperative process and what is an independent process? Let us take that you are, let us say you are Anu or Chitra or somebody else. You are developing an application. In that application, you had altogether 100 processes. All these 100 processes make up your application, in which let us say 80 processes are independent processes. What is an independent process? Independent process is a process in which all the resources are exclusive. That is, main memory space exclusive, and CPU time is exclusive, and also the file systems that are attributed and assigned to that specific process is exclusive. But let us say the remaining 20 of the processes are dependent processes. What are the dependent processes? Dependent process can also be called as cooperative process. Let us define a cooperative process. All these cooperative processes will have a specific section within the main memory, specific space within the main memory that is going to be shared among the others. That means that all these 20 processes will have some common shared area within the main memory in addition to their exclusive area. For instance, all these 20 processes will be given with some space, exclusive space only for those processes, in addition to which all these processes also has some shared memory. So every process, when want to update the shared variable, update the shared memory, they need to make sure that they are that is the only process that is updating the shared memory. So understand this one. Let us say this is a process. When this process is executing, and that too when it is executing in a specific section of code, that shared memory will be accessed. If it is not executing in this specific section of code, that shared memory will not be accessed. So we need to make sure, being an application developer, we need to make sure that only one process enters into the critical section at one time. For one instance, only one process is allowed to enter into the critical section. If more processes allowed into their respective critical section, there will be chaos because there will be inconsistencies in updating the shared variables, updating the shared memory, right? So in order to avoid that, we need to protect the critical section. Being an application developer, we need to protect the critical section. So here, every time when I have to protect a specific critical section, I need to look for some solutions. I need to search for some solutions, using which I'll be able to protect my critical section. But let me tell you something. Any solution starting with Peterson solution is going to incur some or the other problems. I'm not including semaphores here, but Peterson solution or the other solution. Let us take an example of Peterson solution. Peterson solution, if you want to use to protect the critical section, that doesn't work. Simply because the Peterson solution cannot work on the modern days architecture. What is the modern days architecture? Understand something. Peterson solution was developed way back in 1970s or even before that. I don't exactly know when it was developed. For a 1970s computer system, a RAM is of 256 MB and a hard disk is of, let us say, 26 GB or 32 GB is an advanced system. So, every system is an advanced system to the Peterson solution what we are using right now. All the system that we are using right now cannot be using Peterson solution. Simply Peterson solution cannot be used in the modern days architecture to protect the critical section. Now our topic is not about Peterson solution. Let us dive into designing a hardware lock. So let us start. I need to protect this critical section. How to protect the critical section? I will have two gates. One is entry section, one more is exit section. Before I open the gate, I need to make sure that only myself, only this process PI is entering into the critical section. If already one more process is in the critical section, I won't be allowed to enter into the critical section. Upon leaving this critical section, I need to admit that I left the critical section. If somebody else is waiting to enter into the critical section, they may do so. So in this way, the total critical section will be protected. Once again, understand, when a cooperative process wants to enter into the critical section, it needs to make a request. What is that request? I want to enter into the critical section. If anybody else are already in the critical section, please let me know. I won't be getting into the critical section. If nobody is in the critical section, I want to enter. This is going to be from one process perspective. All the processes, when they want to enter into their respective critical section, they need to make a request in such a way. Okay, so now let us understand a beautiful premise which is called a hardware lock. Now this is a shared memory. On your right hand side, we do have a memory in which the white portion, this is the shared memory. When a few processes, all these 20 processes are executing, this shared memory will get accessed. And this shared memory should only be accessed by one process, because let us take a variable. A variable A is a shared variable. Let us say the process A is performing A++. Process B is performing A-. When both are performing A++ and A-, continuously, simultaneously, there will be an inconsistent update. So only one process is allowed to use the shared memory. Okay, now we are going to design a hardware lock. What is this hardware lock? We are the application program developers. Any of you is going to become an application program developer. And the biggest problem in the application program developing is protecting the critical section. What is the critical section? When a process executing in its critical section, shared memory will be accessed. So we need to use some or the other premise to protect the critical section. Looking at the problem of these application program developers, the hardware developers, the CPU developers has come up with one solution which is called hardware lock. Let us see how this hardware lock is going to be designed. A hardware lock is provided by the CPU designers. Of course, approach is very complex and quite simple to use. This approach is designing the lock is somewhat complex. I can't say it is completely complex, it is completely complicated. But usage of this lock is fairly simple. How? I'm going to explain. Let's brace up and design a lock. Now, understand something. In the CPU, we do have a few registers. What are those registers? I do have a general purpose register. General purpose registers such as R1, R2, R3. Why we do have general purpose registers in the system? Every time when you want to update any variable, one of these general purpose registers will be assigned. For an instance, you declared A. Every time when you want to update a variable A, one of the general purpose registers will be assigned. These are the general purpose registers which are given for every variable when it is getting updated. On the other hand, I also do have something called special purpose registers. What is a special purpose register? A special purpose register is designed and used within the processor only to store a specific value. It is not allowed to take any value such as program counter. What is program counter? The program counter can only hold the address part of the next instruction. Alright? So, understand. When you look at the processors register, all the processors register can be divided into either general purpose register or the special purpose registers. Now understand. I am going to, being a hardware developer, being a CPU developer, in order to design the lock, I'm going to implement one more register which is a special register. It is neither a general purpose register nor a special purpose register, but this is a special register which actually is the lock itself. So this is the register what I'm talking about. This is a 1-bit special register. The size of the register is just 1 bit. And it is neither a general purpose register nor a special purpose register. A locking premise to protect the critical section. That's it. If you want to design a hardware lock, what you need to do is, you need to have one more register accommodated within the system. That register cannot be classified as a special purpose register or a general purpose register. But this is exclusively for locking premise, exclusively for designing the locking premise. Just accessible atomically. What is atomicity? Now understand. When this register is being accessed by one process, the register cannot be accessed by any other process. This is what atomicity. For instance, I am a process and one of you guys watching, you are another process. Both of you people want to enter into the critical section. For that, both of you people want to check for the value of this register. We can initiate a search, we can initiate a check of the lock simultaneously, but eventually this register will only be accessible by only one process, either for yourself or for myself. This register will either be provided to you as a lock or provided to me as a lock, but not both. This is what atomicity is all about. What is atomicity? Only one process will be able to access this lock. Although two processes simultaneously want to access the lock, only one process will be succeeded in order to get this lock. In getting this lock, the other process will be queued up. If you want to use the lock, understand carefully. Let us say you want to protect your critical section by using this lock. There is one restriction or a constraint in order to use this lock. If you want to use this lock within your application, within every cooperative process, you need to declare a variable lock of a type boolean, initializing it to 0. Again, every cooperative process need to be provided with a variable lock type boolean initialized to 0. Now, so understand carefully. This is the lock definition. How the lock is going to be accessed, first of all, understand. That lock will be accessed by a function. This is a hardware function. This is a hardware method called test and set. This test and set function is going to use the lock, is going to provide the access to this lock. How? Let us have a look at. Here, we are going to define a function of type boolean. The function type is boolean. The name is test and set. Here inside, we are going to use a parameter which is called target. This target is the actual lock. Inside, what exactly is going to happen is, the initial value of the lock will be passed to a return value, will be passed to a temporary variable within the function. Let us say initial value of the lock is equal to 0. Okay, when a process tries to access this lock, the initial value of this lock will be passed to the boolean RV. Since we are going to access this lock by using a parameter here. What is the parameter? Target. And here the argument is lock. When the lock is passed as an argument to the parameter, what exactly is going to happen? This target eventually which is going to represent the lock, is going to represent the lock for this entire function. Now look at the definition of the function, in which star target, which is the actual value of the lock, will be passed to a local variable which is called RV. Now RV is equal to 0. Finally, we are going to return RV out of the function. That means that every time when this lock is called, this lock will be passed to a local variable which is called RV, and finally the function returns RV. So that means that whenever you call this specific function, the function is going to return the actual value of the lock by the time it is called. Meanwhile, this lock will be set to true. Okay, so initially the first function, the first process, when it wants to access this lock, it is going to find the lock value is equal to 0. Right? Because target, of course, the lock is equal to 0 and this target is being passed to RV, then RV is equal to 0. Finally, we are going to return RV which is equal to 0. Meanwhile, we are going to set this lock to true. Okay, so this is the definition of the lock. Now let us understand how we are going to access this lock. Of course, this lock is executed atomically. Return the instant value of the passed parameter and set the new value of passed parameter to true. The instant value of the passed parameter. What is the passed parameter? Passed parameter is lock. What is the initial value? Initially, the lock value is equal to 0. First time, whichever process wants to call this lock initially when it is equal to 0, obviously this function will return 0. But when it is called, this instruction is going to set the lock to true. So when one process, of course, grabs this lock, it is going to set this to 1 and it will be able to enter into the critical section. Every other process which wants to enter into the critical section will have to wait. How? Let us see. Solution using test and set. This is the critical section. I want to enter into the critical section. How can I enter into the critical section? This critical section should be properly protected by using this lock. So what I need to do is, I need to execute an instruction while test and set lock. What is lock? Lock is equal to 0. Initial value of the lock is equal to 0 at least. So I am the first process that want to check the value of the lock. I am the first process. Nobody entered into the critical section. Obviously, when I call this, what exactly is going to happen? When I call this, let me show you. What is lock value? Lock value is equal to 0. When lock value is equal to 0, of course, target, this actually represents the lock, and this target will be transferred to RV. Finally, we are returning 0 from here. Meanwhile, the target is equal to true. That means that function is going to return 0, right after which lock will be set to 1. Here, when the first process tries to access this lock, and of course, it will be succeeded in order to access this lock because the lock value is equal to 0. So, the first process will be able to enter into the critical section right after it sets the lock to 1. Okay. Any other process which wants to enter into the critical section right after the first process already is in the critical section, they won't be able to do so because they will get caught up in the infinite while loop. Because of, you can see this, while test and set lock, if lock returns 0, this condition fails, the first process enters into the critical section. If the lock is equal to 1, obviously when one process P1, let us say, and is in the critical section, this lock value is equal to 1. Second process, let us say, it wants to enter into the critical section. It won't be able to do so because lock value is equal to 1. It will loop around. It will get caught in the while loop. Now, the moment the first process finishes with the critical section, it should come out of it. Right? Of course, infinite loop. If the lock is not available, any process should be caught in the infinite loop. Now, when a first process, our P1, the moment it finishes with the critical section, it will come out. After which, it will say lock is equal to false. Any other process which has got caught at the while loop will be able to come out of that while loop and enter into the critical section by making the lock value to 1 again. So, this is how a lock is going to be designed. Fine. Understanding this function is not a biggest deal, but the implementation part is really important to understand. That is, we're just using a processor's register, that register cannot be assigned to any other variable. That register will only be assigned to a variable which is called lock. And that too, if you simply declare a variable saying lock, it won't be assigned. This lock should only be used and accessed by using this test and set function. If you use it in association with the test and set function, then our special register, I would say X, otherwise I would say L, will be assigned to this lock. Okay, so as the lock value is equal to 0, this L value is equal to 0. And once after one process enters into the critical section, inside our register value is equal to 1. Any other process which wants to enter into the critical section using this lock, using this test and set premise, will be able to find out that this lock is 1. That means that lock is already been closed by another process. This is what the correlation between hardware and software. Unless we actually have a complete idea, complete transparency what exactly is happening within the software, we will be kind of in a soup. We don't understand actually what is happening inside. So it will give you the ample clarity how to use this lock. That's it from this session. Aneel Prasad Surampudi signing off. And please like, share this session and subscribe to this channel if you haven't already yet. That's it from this session. Aneel Prasad Surampudi once again signing off.